Good evening, everyone. So my voice is audible.
Hello.
Yeah, hi Vinay. Is my voice is audible?
Yes, your voice is audible. What you are to Ashutosh? Please start the session.
Definitely. So yeah, thanks Vinay for that introduction. And good evening, everyone. Here Ashutosh Raj from the Decibels Lab Private Limited. A warm welcome to you all for the participating in the today bootcamp. So today in this today bootcamps, we will deal with the modeling of the battery, especially equivalent circuit modeling, and how to get the model parameters from a test. Okay. So especially we will deal with the DCIR test. Then we will go forward with validation and the separations of the MATLAB and Simulink. So yeah, let's start. So for the student boot camps, I will go through like these are the contents. The first like introductions about the modeling basics, then about the understanding of the DCIR, what DCIR is there, then about the DCIR testing methodology, then what the factors this affects to these internal resistance, and then how to extract these parameters from the DCIR test, then equivalent circuit modeling and simulations, and then conclusions. Okay. So yeah, what is modeling? So modeling of any battery is basically it involves representing whatever the dynamics processes or what the process is going inside the battery to just model in the terms of equivalent circuit. Okay. So for the battery, we know we have a voltage response. Okay. So when there is some current input is there, so when we charge or discharge the battery, so there will be some voltage response, and that voltage will vary with time. Okay. So how to model this voltage response, the variation. So there is a model. Okay, so this model we go through like equivalent circuit modeling. Okay, so this is not only one model. We have a different types of the models. So some are physics based models, and another is like data driven models. Okay, so but basically here in this today's sessions we will go through only equivalent circuit model. So equivalent circuit model is basically what it is. There. So it represents like it uses resistor capacitors and voltage sources to mimic the what the behavior is battery is showing. Okay. So usually we know battery we have a when we test the battery we get there some voltages. But with that voltages there are some resistance is also associated. So how to model those resistors? Okay, so how to model those resistance? We can mimic whatever the physical processes, all the things in terms of resistor capacitors. Then in equivalent circuit models, we have a different varieties, not different varieties, but I will tell you there is one specific equivalent circuit model name is there that we call as a Thevenin model. So already we know that any complex circuits we can model in the terms of the Thevenin model. So same here, the battery we can model in the terms of the Thevenin model. Okay, so what it basically so it's a combination of your open circuit voltage that represent the battery OCB and then the internal resistance associated with those battery. So those resistance we can model through your R0, R1 and C1. So here one branch of R1 and C1 is there. That's why we are taking so one RC model. If we will represent with the two R1 and C1 branch, we will go through two RC. So we can also, whatever the physical process is going on, it cannot be possible to model in terms of only one RC branches. So sometimes it requires lots of n branches. Okay. So for those polarizations, we need to go with the more number of RC branches. Okay. So how we will go through those? We will go through the using the ladder RC networks. Those are specifically used for your diffusion simulation. So now we have gone through like what equivalent circuit is there. But to model, we need to, for those models, we need to get the parameters for those model parameters. So those model parameters, how we will extract? So we need to test those battery. Okay. So for the testing of battery, some simple ordinary ways like multimeter. If you will connect your positive terminals with positive and with negative, you will get your OCB values. Okay, right? Then we have a ACR testing. Okay, and there is a one pulse based test. Okay, so these tests are basically for your resistance interpretation, like to just test the resistance. So ACIR is like AC based test. There we just connect the battery to the ACR instrument, and that we purge. AC excitations at a high frequency at a 1 kilohertz, and it will show you whatever the internal resistance the battery is associated with. So you can see here in that figures, you can see here where the person who has connected this battery, and in the red color it is something showing the OCB is showing around 3.264, and the resistance associated with it's about 3.61. Okay, sorry, 3.264 is your resistance, and then 3.61 is associated with your OCB. So similarly, we can also test battery in the terms of DC based. So DC based means what? We need to excite through the DC current. Okay. So through DC current, we need to excite the battery. Based upon that, we will get the variations of your voltage. So there is a one test we call pulse based test. So in that category, we call it like as a DCR test. Okay. So DCR test is a pulse based test. So from fully charged battery to like whatever the your voltage window is there, from full charge to the lower voltage limit, you will discharge the battery, okay, through the pulse, not continuously. If you will go through the continuously, it is like a static capacity test. So with variation of your pulses, like you need to go through the full discharge of the battery, and you need to just go through like what the voltage response is there. Okay. So and those voltage responses, again you need to check it for your parameter calculations. If anyone has a doubt, you can put them in the chat box. Okay, at the end of this sessions, I will go through all your doubts. Okay, so in Decibels, we have all the facilities of the battery testing. So we have a different battery testing with the 100 amps, then 50 amps, then 5 amps, all of the battery cycles. We have the facility with along with all we have a facility of environmental chambers also. Okay, with that, we have also facility of EIS, electrochemical impedance spectroscopy, and for the battery pack testings also. And then we have a ACR instrument. So all the tests associated with the battery we can go through. We all have the facility in our Discord lab. So what the DCIR is here? So DCIR is basically the stand for your direct current internal resistance. Okay. So it is the internal resistance of the battery which is measured by applying a DC pulses. Okay. So when you excite the battery to the DC pulses, we will see in the voltage there will be some voltage drop will be there. Okay. So those voltages drop, we need to parameterize or we need to fit it to extract those parameters. So simple case I have given here. So we have a one current as a discharge current, one pulse is there. Okay. So with associated with this pulse, we can see here like we have a voltage drop in those durations. Okay. So how we will calculate? So basic is based upon your Ohm's law. Okay. So whatever the voltage changes like from V2 to V1, and then what the current that we have excited or the change in the current. So when you will divide through the change in the voltage terminals like V2 minus V1 with the current excitation, you will get your simple resistance of the battery. Okay. So I have given here one example how to go with the DCIR measurement. So as a numerical, you can see here, first we need to just provide some current pulses. So here I have given example as a 10 ampere. And then voltage drop we observe like from 3.7 to 3.65. And when we just calculate through, we are getting 5 milliohm over our DCI. Okay. So what the physical process is going happening? So you will observe there, like when you will just excite through the DC pulses, there will be some instant drop will be there. Okay. So that instant drop in your voltage, it will be associated with your ohmic resistance. Okay. Then it will be only for the fractions of seconds, like millisecond in that only. After that, if your pulse duration is more, like it's 10 second or more than 10 seconds, then only you will observe those polarization. Okay. So usually we provide pulse more than 10 second. Okay. So for HPPC, we provide the 10-second pulse with a high current amount. But here we will not go with the HPPC test. With SOC removal, the pulse associated with your SOC removal, we will go through only that. Okay. So in that durations, there will be some instant drop in the voltage that will be associated with your ohmic drop. And after that, there will be some exponential decay like structure also that it's associated with the voltage polarization. Same thing when when again you will cop that current excitation means it will be in the rest. Again, during the rest condition, sudden rise in the voltage you will see. Okay. Then again with the rest condition, there will be like in the relaxation mode, again your voltage will rise to some different potential level. Okay. So DCIR is basically we have an instant voltage drop which is associated with ohmic resistance. Then there will be gradual voltage drop that will be associated with the polarization effect. So we can tell here like DCR is not that one value. It is associated with all full values like ohmic resistance. Then some resistors drop because of polarizations. Okay, so in that polarization there is a two category. One is your charge transfer based and other one is a diffusion based. Okay, so what are the factors that DCIR those internal resistance is affected? So first it is affected by like your SOC. So at a higher and lower SOC, we will mostly observe like you will get higher internal resistance. Again, with the temperature variation also, at a low temperatures, that resistance increases. Because why? Because of those the electrochemical kinetics or the processes which is going on, it got slower. Okay, at a low temperature, your electrolyte, then the conductivity through the electrolytes and through the electrode materials, that will be not that fast. Okay, so it got slower. That's why we observe it's a higher we observe it as a higher impedance or as a higher resistance. Same thing with the C rate. So when you will go with the charge or discharge the battery with a higher C rate of thing, okay. So in that time you will see there will be sudden large amount of drop in your ohmic drop. Okay. Why? Because your current is increasing and based upon that E is equal to IR. If you will increase your current value, so the associated voltage drop will be higher and associated with that your resistance will be also higher. But mostly these higher current based excitation, it will mostly affect your polarization effect. Okay. Then again with the your state of the health, aging, especially when your battery will age. So with the aging, your battery, whatever the materials it will got degraded, and because of the we will get some changes in the resistance. Okay. And with also with like pulse durations and those with the different cell chemistry. Okay, so here we have tested with Samsung 18650 2.6 ampere hour NMC cells, and we can see observe here your cell internal resistance at a higher SOC and the lower SOC it is how it is varying. And with cycle aging, we can observe how your internal resistance is changing. Now we will go with like a DCR testing. So what DCR test is basically? Okay, so DCR test we especially perform by applying the control current output. Okay, so it is not here like we are just exciting. We need a controlled current pulses. Okay, and this DCR we perform from at a perform at a particular SOC. Okay, so if you have a 100% SOC, you can perform your DCIR, and from 100% to 0% SOC, you can also perform. But in that ranges, you need to change your SOC also. So it may be your 5% based SOC removal or 10% based SOC removal. Why? Because we want to observe all the internal resistance associated with at a particular interval of SOC. Okay. So to determine your internal resistance at a specific SOC level, so cell must be discharged at a defined C-rate. Okay, it is not like randomly you can put any discharge. You need to particularly at a what particular C-rate you will be go through discharge pattern. And again with the specific duration. Okay, then the thing is that that current pulses, if you want to remove the whole SOC, so these pulses must to be repeated. Okay, so in the next slide I will describe why it is this. So you can see, observe here, there is a one pulse. The battery initially it was at 100% SOC, and now we want to remove the 5% SOC so that our cells will get till 95% SOC. So there is one numerical I have shown here. So if you will go with a 2.5 ampere of discharge current and you want SOC removal of 5%, so if you have a capacity already measured at 2.5 ampere, you are getting 5.17. So from here you can calculate like the 5% capacity of your total capacity. So we are getting here 0.2589. So now to remove this 0.2589 capacity, we need the required discharge time. So we can calculate T is equal to Q upon 5. And based upon that, we can calculate no 6.22 minutes. We need to just put the pulse durations. So when we will just go with the pulse durations, it will just remove your capacity with 5%. Same thing with your in the charging mode also. Okay. So now we need to remove all the capacity from 100% to till 0%. So for those things, we need to repeat those pulses. Okay, so earlier slide, it was just for a one pulse, like for that pulse, how much duration is to be there and what the current should be there. But suppose that if you want to go from 100% to 0%, those pulses to be repeated. Okay. So if you have a 5% of associate step or 5% of associate interval you want to remove, like 100, 95, 90, 85, then 21 times you need to repeat those pulses. Okay. So when you will repeat all the 21 times of your SOC, you will get like voltage variations in all those associate intervals. Okay. So now here in the figure, you can see here, like with full SOC removal from 100% to 0%, you can see here how your pulse is going on. So with all like at 100%, 95%, 85%, in all those pulses that with that associated some voltage drop will be there. Okay. So I have shown that region at the zoom level. You can observe here during your pulses and then during your relaxations. Okay. So after each and every pulse, we need to put some relaxations. Okay. So usually we put 1 hour of relaxation. Okay. Then after 1 hour, we switch to the next step, like the current that repetitions. Okay, so here the response of your voltage analysis I have shown in the two figures. Like one is which is highlighted with the blue one, which is related to your discharging, so during discharge conditions, and then another one which is yellow, it's a no load condition. It means that during relaxation. So RC values of the equivalent circuit, it can be derived by analyzing any of these two. Okay, so how we will analyze the next slides I am showing here. So usually what happened if we will extract the parameters during the pulses. So we know that during the pulses your cell is discharging. So in that discharging, your voltage will be also fluctuating, it's also changing. Okay. So if you will extract the parameters from that during discharging, you will not, there is no chances to get your accurate parameter. So better to extract the parameters during relaxation. Because in the earlier slide, I've shown you during relaxation mode also, you are getting here one IR drop, like the instant voltage drop is there. And then after there is some polarization effect. Those effect, it is associated with your relaxation. Okay. So we can see here, like if you have a relaxation mode in the relaxation region, there is a sudden current or voltage increment in there. It is associated with your ohmic drop. And then that relaxations, okay, after that instant drop, there will be some voltage relaxation will be there that will be associated with your polarization region. Okay. So now how to extract those parameters? So for the ohmic resistance, it's the basics. You need to just difference to get the difference values of your like V2 to V1. Okay. And with the divider of the current or the value of the current you have stated, based upon that, you will get your ohmic resistance. Here as a one numerical I have shown you. So during the tested, your voltage was gone through like this changes. So based upon these changes, we got 0.0197 ohms. Okay. So getting ohmic resistance is easy, but getting your polarization based resistance, okay, those are very difficult because those are based upon your exponentials. Okay, capacitors is there. So those capacitors, it will show transient behavior, those things. So we cannot directly calculate like V3 minus V2 divided by I. Okay. So we need to fit those exponential curve through your RC parallel terms, means like your RC circuit. Then you will get to R1 and C1 parameters. So to get R1 C1 parameters, first we need to understand what the time constant is here. So basically time constant, it represents like how fast the RC branch that voltage build up during a pulse or the during your relaxation mode. So what happens when you discharge the battery, you will observe that voltage drop will be there. Okay. So that voltage drop, some parts of that voltage drop will be associated with your ohmic drop. Remaining voltage drop, it will go to charge your capacitors. Okay, that's why you observe there is a change in your voltage. Okay, so what happens? Your capacitor will charge. Okay, so that charge build up, that your potential will build up across that capacitors, and that will be associated with your some drop. Okay, so we observe in our pulse base. Same thing here when we stop the excitation, sudden drop will be there, and then we will see like voltage increment will be there. So that increment will be associated with your RC branch, that whatever the voltage it was earlier it was associated. So now capacitor and RC branch, it will start to discharge. So that discharge, will act like as your potential will increase. Okay. So for those phenomena to get through, we need to go with like how fast like your voltage will build up or voltage will go through. So those things is associated with your time constant. Okay. So yeah, so we have a one short time constant and a long time constant. So short time constant is associated with the fast response. You can see here when after this plot is basically after overdrive. So you can see here it's a 4.03 and then 4.08. So I have taken this only part. Okay, 4.082 OCB mode. You can observe here for 4.082 OCB mode. So in there you will also observe there will be some sudden changes in your voltage. Okay, so whatever the like how fast it will be there, it will also go out of. So the time constant associated with this response will be considered with you as a short time constant. And later on, whatever like there will be no that much of change in the voltage. Okay, so those is associated with your long time constant. Okay, so time constants. Again, how you will get those time constants? So basically, time constants are obtained from your cell transient voltage response. So we need to go with the cell transient voltage response. So what the transient voltage response? Okay. So transient voltage, how we will get? So transient voltage, we will go through. Like suppose that at the end of your voltage, you will get some OCB values. Okay. Then OCB voltage, you need to subtract with the each and every point. Like I can show here as a P1, P2, P3. Okay, so whatever during the relaxations mode, you have all voltage curve are there. So you need to extract with the final value with the each and every values. Then you will get your transient voltage. Okay, so transient voltage it is not like as a measurable quantity. It is just for the mathematical like you need to calculate. Okay, so it's a difference between your OCB minus each and every whatever the points of the voltage your machines can go through. If you will just subtract this, you will get your transient voltage. So here you can see like we have a cell voltage response to visualizations, and when we just subtract those OCB with all the voltage points, we got our transient voltage. So the behavior of transient volt you can see here, it is also exponential decay in nature. Okay, so how we will go through? So we know if we have any exponential decay there we have exponential function. So at any time you want to get your transient voltage, you just put with your final value, okay, and with the exponential function. So suppose that if you want to calculate the transient voltage at any particular, like in the any time region, like if you at a t end, okay, so t end basically denotes any point here, okay, it is a transient is started here and the transient will decay to zero here. So this is a transient or a stop with here. So we can observe here when your battery is just a sudden drop is there, your transient will be too much high, okay. Then with like as go with the relaxations, your transient will also decay, and at the end it will decompose to your zero. Okay, so in a particular region, if you want to calculate, we have a given formula Vi t. Just it's a just exponential. We have derived in the terms of one a particular time range. Then if you will take the logarithm with a mathematical calculation, you can get your time constant. So it basically is like the time ranges divided by your logarithm of the starting of your transient voltage divided by your end of the transient voltage. So what the time constant is now? Time constant is basically the time required for the transient voltage to decay to 36.8%. So if your initial value is some, okay, here, if you will get there, then in that duration, it's 36.8% it will go. We will call as a one-time constant. In your cell voltage realization mode, where your voltage will go to 63% of your final value, we call as a derivative time. Okay, so with the cell voltage response, it is 63.2%, and in the terms of the transient voltage, because transient voltage is decay in nature, we will get 36.8%. So for your initial. So here one numerical I have given how to just go through. So we have a TS stars, okay, and we have associated voltages there. Based upon that, we can extract your transient. So here we got our time constant value as is 68.4. Okay. Again, one thing I want to put a stress on that. You don't need to go through the end value of your time. So it should not to be like nearby zero. So you need to choose those ranges which is not able to go where tangent to decay. So it should to be range of where some transient voltage is there. So I have taken with 100 seconds. Okay. So in that duration, you can see we have a 68.4 seconds of your transient. Now with this transient or with the time constant, now we will able to get our R1 and C1. So Okay, so how R1 we will put? So R1, we know that in RC circuit, if you have a parallel RC circuit in a battery, so there will be some initial voltage will be there. Okay, so during pulse, it will be have a some initial voltage, and with that initial voltage, there will be some transient associated with it. Okay, so we will calculate our R1 to the initial transient voltage. It was there across your RC branches during the pulses. Okay, so that VRC, if you have initial, the whatever voltage across was there, it will be same as when the transient it is started. Because capacitor, it will, it doesn't sudden changes your what the voltage is. So when you will go start with the rest conditions, at that time also what the capacitor earlier voltage was there, it will be same. Okay, so based upon that we can see here, we have already calculated at a VI 0.0238 voltage was there when the transient was started. So we utilize that transient voltage to just calculate what the your R1 is there. So if we will put here and we will put your time constant. So based upon that, we can see here VRC, like initial voltage across the RC branch, we got 0.0234 voltage. So now when we will put this initial voltage across, from that we can get our R1 resistance, which is basically it's around 9 million. Then we already know there is a one time constant R1 C1 relation is there. And through this relation, we can get our C1. Okay, so from C1, when we will divide our time constant with the R1, we will get our capacitance value also. Now we will go a bit like how to develop the model and how to just go with the simulation part. Okay, so you can see here, if we have a battery, okay, so we can model it as a one RC circuit. So for two RC circuit, we have to go with the two RC branch. So basically here, just for the simplicity, I am just going with the one RC model only. And you can see here, we have developed our model here. Okay. So for these one RC models, we need to go with like how to estimate those models parameters. Okay. So we have to go with the SOC estimations, like OCV estimations, then how to estimate internal resistance, then polarization estimation. Okay. Then capacitance estimations. These values are not only dependent on SOC, it is also depends on temperature. So what the models we will build, it will be also dependent on temperature also. Okay. So now I will go through the MATLAB and I will show you like, so yeah, I'm not going to develop the model because it is not, uh, we cannot deal with in this bootcamp. It will require lots of struggles and those things to build this model. Okay. So it will require 1.5 hour sessions to just go through how to build this model. So I'm just showcasing you like we have developed the models. Okay. So for the SOC estimations, we have utilized the Coulomb counting method. Okay. And then for your OCD, this is the estimation based upon the lookup table. Okay, why we have used a lookup table? Basically, what happens when we calculate OCB, it's all will be in the particular ranges, like at a 5%, 25%. But we need to simulate in the like continuous forms. So lookup table, it will convert your like two discrete value as a one continuous. That's why we are using the lookup table. And for those lookup tables, we have used with because we know that OCB are not those parameters also dependent on your SOC and with the temperatures. So we have utilized 2D lookup table. Okay. Then same thing with your internal resistance also. Okay. Then with capacitance estimations, same thing. Okay. Then with your polarization resistance, just it's a basically you're just giving through, and there will be some uh, interpolation will go through, and based upon that interpolation, we will get our carbon values. Okay. Then terminal voltages. So for the terminal voltage, we have equations like VT is equal to OCV minus whatever the voltage drops across your resistance. If your ohmic I minus R, okay, then sorry, minus IRO. Then with the capacitors, there will be some associated voltage drop will be there. So there's a one equation, and through that equations, we have built up that models, and through that build up models, we got here our terminal voltages. Okay. Then all things I have connected to one scope. And same thing, because we know our model is dependent on temperatures, so we need to also estimate the temperature. For the temperature estimations, I have gone through. So it also gone through. So for modeling these temperatures based events, it takes me a lot of times and lots of like I've gone through. Then only I got those models. So we cannot go through like to develop the model. Maybe the next any boot camp will be there. It will be more associated with your how to develop the model. Okay, like how to estimate yourself, cell temperatures, those things. But today in the sessions, I will only more focus about like how to just go if you have a model, how to validate this model for different current profiles. Okay. So yeah, this is the model we have developed. Okay. Then now to just like to validate this model, we need to extract the parameters. Okay? So how we will extract the parameters? So parameters we will extract from the real test data. Okay. So yeah, we have a some DCIR. Okay. So this is your static capacity based on test data. We have performed at a zero point 0.5 C rate at a 25 degrees Celsius and a 40 degrees Celsius. And then we have a DCIR data. Okay. So this is the profile which is associated with your DCIR. Okay, so we have performed TCR at a zero point 0.5 C rate at a 25 degrees Celsius and 40 degrees Celsius, and then at a 1 C rate at a 25 degrees Celsius and 40 degrees Celsius. So the model parameter is set from only with this real test data. Okay, so we need to go with and we need to extract the parameters from this Excel sheet. Okay, same thing here. You can see like we have also go with your OCV. Okay, so static capacity based OCV calculation and then DCR based. Already I have calculated. Okay, and then we have a DCI profile. You can see here we have a DCI profile. So okay, from 100% SOC to 0% SOC at a 0.50. Okay, so now I will showcase you like how to extract these parameters. Okay, so yeah, I will not go through like a script because I know it cannot be able to just include all the things within 1 hour because already we know that bootcamp session is for the 1 hour. So maybe in the futures I will more focus on I will plan one bootcamp where I will more focus about how to develop the model and then how to write the script, all the things. Okay. So here just one basic scripts I have written here to extract the parameters. Okay. So yeah, so how we will go through like we need to read those Excel sheet. Okay. Then through this Excel sheet, we need to go with the step ID and voltage. Then with those step ID, we need to find about what the steps ID it was related with your load and then with the OCV and how with those steps, your open circuit voltages and terminal voltages are there. And with those, we will go to and then SOC. For SOC, I've written a script like with the variations of 100% to 0%. And then for the transient voltage calculation, we will utilize our okay for loop and so here we can see like because we have relaxed our cell for a 60 minute or that's why we have taken here 360. So this is our first index of our relaxation is equal to 1 and this is the stop of the index point. Okay, relaxation. So in an Excel sheet, it's a whole about when your relaxation started till the relaxation ended. So in that, we need to find our relaxation voltage. So we have based upon your code loop, we have written some script. Okay. Then with each and every SOC, because we want to extract those relaxation with each and every SOC, that's why we have gone through this form. Okay. So here it's not like with the next SOC. Same thing with your transient also. So we have started with the transient. Okay. For all 21 sets of your SOC removal, we started with like how we are calculating transient. So we are calculating transient with your relaxation minus your relaxation voltage at the start with the relaxation voltage at the end of relaxations, your OCV is there. Okay, so we are subtracting, and from there we will get our transient. So these transient voltage we need to calculate for each and every SOP. So we have written this script for all SOP. Then the time constant calculation. So here I have also put a time constant as a 100 second, and based upon that I have calculated a time constant. So at the beginning of your time constant, you have a some VT1 value to be there, and at the end of your time constant, you will have associated with your VT2. Then we will get like T2 minus T1 divided by your logarithm of your voltages. Based upon that, you will get a tau. And then for your initial voltages, what voltage is there? So expressions of formula I have already shown the slides. The same formula we have written here just to calculate your initial voltages. Then ohmic resistance, how to calculate from these values. So ohmic resistance, we know just only V2 minus V1 divided by whatever the current. I already mentioned whatever the cell I have, I am using it's 5 ampere. So at a zero point 0.5 C rate, we need to put current value of 2.5. Again for the polarization resistance and the capacity. Now I will just simulate this to get like what the parameters it will extract from our Excel sheet. So which Excel sheet? Like this is the DCIR test Excel sheet. So already I have shown you like DCR Excel sheet. So in that we have a 25 degrees Celsius at a zero point 0.5 C rate. Okay, so from you can see here we have a step IDs, and then if you will go through the step four, sorry, step ID four, you will go through the relaxation. You can see observe here the current value is nearby 2.5 to 2.4976, and the associated voltage is there. Okay, so what will happen that MATLAB it will go through and it will read these Excel file, and in that Excel sheet, it will just go through and it will capture, it will find those steps associated with your pulse and associated with your relaxation. And from that, it will calculate based upon the formula what we have given here. Okay. So yeah, I think that still it is like running. Yes. Okay, I can compare it is saying that's way. Okay. Maybe I think because it is open, that's why it is not saying. Yeah. Okay. So yeah, if it is taking time, already I have gone through and I have accepted those parameters. So you can observe here, like how your R naught values and those things, it is changing. Okay. So you can see here your the estimated R naught, R1 and C1 from those Excel sheet, and also with your temperature variations also, like how it is changing. Okay. So ultimately, I think at the end of this value, that this MATLAB, it will do these only value. Okay. So one more I will try with it. Be able to fit for the result. Meanwhile, I will go through like how we have extracted or what happened like when we just got those data. MATLAB, it will show here in this workspace all those are not R1 C1 values. Okay, so those values we will use for parameterization of our model. Okay, so for the model development, I will go through one script. I will show you how to we have written this script. So you can see here like this script we have written for the MATLAB. So this script is related with like because we already know our model is dependent on temperature. So whatever the script we have written for the parameter extraction, the same thing with the 25 degrees Celsius and with the 40 degrees Celsius. Okay. Then also the transient calculations with your 25 degree, 40 degree, and time constant also with 25 and 40 degree. So what will happen when I will run this like this script, the MATLAB will give you all data. Okay. So now I think it is like, yeah, you got like see here, you can see here the parameters I already shown you in slides are not R1 and C1 variations with your pool SOC. So our MATLAB extracted those parameters with variations. Okay. So with each and every SOC, there is associated some R not value will be there. Okay. So these are not value we will utilize here. So you can see here, here in workspace, they have seen like R naught value, I will show you for R naught value, it is like you have a 21 sets of the values, 21 sets of value for each and every 5% association. So at 100% association removal, then at the end of your association. You can see here, observe it, like whatever the 21 sets of your R naught value. Similarly with R1 and C1, tau, transient, all will be there, the MATLAB. Okay. So now what I will go through, I will just go through and I will run the script just for at a particular temperatures. Okay. So just get on. So these values, okay, I will go through, I will utilize as a lookup table. So you can see here, yeah, you can see here in the lookup table information, I have gone through like how to utilize those parameters with the script. Like from that script, we have extracted the parameters. So how we will utilize the lookup table. So model, we just go through model. In that model, we are commanding from the script only. Okay, so that's why we need to write this script here just to fetch the input in our model. So OCB lookup table, for that OCB lookup table, we have written these scripts for SOC based lookup table that for R0, R1, C1 values, what we are doing. Now why I'm flipping? Because uh, our data is from reverse order. Okay, so we want from like a higher SOC to lower SOC. Okay, that's why I'm flipping this as lookup table. Okay, then with the profile of the 40 degrees Celsius, there's an associated discharge profile in here. So with associated discharge profile, I have already shown you like there is a one DCI profile. Okay, I think here discharge profile. Yeah, you can see here. This is the static capacity data at a 40 degrees Celsius and 25 degrees Celsius. Okay, so this just to validate this, I have written like I've gone through like the MATLAB will read those Excel files. Based upon that, it will plot. And for the simulation of the model, I have written this script. Okay. Why we have put it a stop time is 7834 because we have seen if you will go through if you will observe here at the end of this discharge it will be like 7.834. Okay. So that durations we have set it for our simulations time. Okay. So now what I will just but before that I will show that model. Okay. So in that model that a current because we have exciting with the 2.5 ampere I will just go through and I will just unconnect this. Okay. And then with so now my this model will excite with a 2.5 ampere because we have tested our static capacity at a 2.5 ampere at a 40 degrees Celsius. Now I will go through and I will try to validate the static capacity profile. Okay. So here I will go through and I will just run this. Okay. Yeah. So meanwhile it is running. I will showcase you like with different temperature also we can go through because we have conducted our static capacity test at a 25 degrees Celsius and a 40 degrees Celsius. So now what I am simulating, it is at a 45, sorry, it is at a 40 degrees Celsius. Same thing for 25 degrees associated data. You can also validate. Okay. So here with 25 degrees Celsius, I have written the script. Okay. So here also the same thing. There is no that much changes. Only whatever the Excel sheet which is associated with your discharge of that the Excel sheet that contains that discharge profile, you need to just write down here as a script, and then in the same whatever the discharge time it will be there. So for 25 degrees Celsius, we have observed 7542 seconds set of the. So for the simulations, we have set it also 7542 seconds. Okay, so I think till it is running, I think MATLAB because it is not stopped. So I will showcase you like how this model is validated this static capacity data at a 40 degrees Celsius. So same thing like as a 25 degrees Celsius, you just all the things it will be remaining same because model is a temperature dependent. So I have built a model based upon 25 degrees Celsius and 44 degrees Celsius. So ever part will remain the same. Only during the simulations you need to change like which profile you want to validate either at a 0.5 C rate, C at a different temperature C rate, all those things, you need to just put it here. And then the associated time values you need to put here in your model simulation script. Then it will give you, you also validated that model. So I think it is taking some times, maybe some internet program is there. So I will show you, like I have already gone through. Okay. So yeah, I will show you like for this static capacity at a 25 degrees Celsius, I have performed and you can see here, like our model is validated. And the same thing with your 40 degrees Celsius also, you can see here. So your blue one denote your measured voltage, and then red one is the simulated data. Okay. So with this static capacity, we have validated our model. Okay, I want to check whether now it is showing or it is still running. Okay, so I think this is still running. Okay. Yeah, I think now our model, you can see here, this model, they have given all those values associated with this. Okay. Um, yeah, you can see like at a 40 degrees Celsius, whatever the I have written the script, based upon that, you can see here at 40 degrees Celsius, the blue one curve denotes our result and like real test data. Okay. Like real test data means in the Excel sheet, you can see here. I will show you. It is that for 40 degrees Celsius, you can see here. This is our profile. And this profile, I want to just validate with our developed model. So you can see here, our developed model, it's simulated the same. Okay. So there is some error is there, like there we should know because we are just going with, we are considering only one RC. If it will go with the more RC branches, our model, the simulation will be more accurate. Okay. So in the mid of SOC, you can see here some, there is some discrepancies there. And at the lower SOC, you can see here. Yeah, apart from that, model, it's fitted very well. Okay. Then we can also set our model error calculation. I think MATLAB has gone through. Now I will go through your TCR pulse based script. So in the pulse script, the same. Okay. So what will happen if you have a DCIR based profile is there? That Excel file you need to put here. That MATLAB will go through. Okay. So we have written the script associated with your DCIR profile. Okay, then transient calculations with each and every, and the time constant, the ohmic resistance, all the thing. So what happened is there, these value we have extracted from the DCR profile. Okay, but we are validating for different current profile. So earlier we have just tested with your static capacity test. Okay, but the model parameters we have extracted from the DCI. Okay, it is not, yeah, I think, I mean, you cannot extract the parameters from a static capacitor because here, see, you can see it's continuously voltage drop is there. Okay, so extracting R naught, R1, C1 is very difficult. You cannot extract the parameter. That's why for the same cell, we have performed DCR test. From that DCR test, we have extracted the parameters, and those parameters, based upon those parameters, we have developed we have built the model. Okay, and with those models, with the same cells, we have performed different tests like GITT, static capacity, and the DCIR or HPPC pulse, those profile we will validate with those parameters. Okay. So now you can see here for the pulses, DCR pulses, I have gone through and I have the same thing because from the same pulses we have extracted those parameters. So all ever part is remaining same. Same for the time constant. Here just only I have changed your, okay. So I will just unpack this. Yes, I will correct this. Now for the lookup table, the same thing. Just only you need to go with like profiles. So for the DCI profiles, we have Excel sheet. In that DCI as well, what the total time duration was it has taken. And then based upon that, we will go through and we will calculate. Okay, like simulate, we will simulate, and based upon that, we will plot the figure. Okay, so yeah, I will go through because it's earlier. I will just clear all the things because that was earlier it was related with your static capacity. Now I'm going to perform with your our DCR pulses. But in the model, it is still at a your static capacities. So for the DCI profile, I will connect my model to our DCI profile. I will just comment on this and just comment it. Okay. So here I am not putting any values. Why? Because those values I am giving from the workspace. Okay. So I will show you. So this is your DCI profile, and this DCI profile we have given through the excitation we are going through the pulses. But prior to this, I will just start to run it here so that our product can learn. Yeah, see here you can see here. You can see here like for the profiles, I have set it like which profile we have to go through. So for this, I have given the command for the Excel to read this Excel sheet. Okay. Then the discharge countries as well. And then for the simulations, here you can see the DCI profile is there. Then this DCI profile, what would happen? Whatever that associated time and the voltage will be there, I have given it. Okay. So discharge current negative, I put it because of those negative values. Because we are discharging it, so current value is negative. That's why with associated with we have given our negative sign. Okay. So here with this DCI profile, our model will excite and based upon the simulated like the time we have written here for the stop time, it will go through, and with this in this duration our model will like okay, so it should to be same with your whatever the t-shirt profile is there. If there will be some like suppose that if you will put the lesser value that the plot will be earlier like it will terminate earlier. Okay, so if you want to just validate the whole profile like from 1 second to 83140 seconds, okay, so you need to put, we need to write also here the same kind. Okay. Yeah. So here, whatever the script I have commanded, so from there we can see that the R naught R1 value at a 25 degrees Celsius and 40 degrees Celsius, it has like extracted those parameters, and you can see the differences in your parameters with the variation in the temperature. Okay. So yeah, I think here's a problem was very line 140. That's why it is not able to just go through. What I will go through, I will just command this. So I will do. Okay. And then one more time I will go through. I will try to just validate that our DCI profile. Okay. So same thing for your HPPC profile also. If you have it, you need to just go through and you need to just change here the profile. If you have a Excel sheet associated with your HPPC profile, okay, or GITT profile, just give the command the MATLAB to read those Excel sheet. Just put your variables like what the time associated with there, what the current you have set it. Okay, that column. Okay, the time column, your current column, and then voltage column. Okay, those associated with you need to go through, and then for the simulation of your model, you need to from the workspace you need to go through. You need to put you need to write the script in your DCI. Okay, I will go through and I will free problem. And I think it is still meditating. Okay. Yeah, for the temperature here we have seen like this extracted those parameters. Okay. But I think it is meditating. So meanwhile, I will show you, like I have already tested it. So you can see it here, like for a single purse, we can see like our model has validated. Okay, there is some differences there because we have only considered as a one RC. That's why some differences there. It is not overlapping or it is not like overlapping with our user data. Okay. Same thing for your DCI profile. You can see. So I think it is now validated. Yeah, see, yeah, you can see here, like at the 25 degrees Celsius, we have performed our DCI test from 100% FUC to 0% FUC. So our measured test profile is your red one, and the model that we have given the command. Okay. So based on that, we can see here it is pretty good. It's validated. Just those diffusions, like during the relaxation, we can see here there is too much of error is there. Okay, it is not well overlapped. Why? Because for those diffusions related phenomena or the processes, we need a more number of RC branches. Okay, so when you will go with the 2 RC, 3 RC, 4 RC branches, those voltage error, it will be minimized. Okay, so I will show you like how to just go through and how to calculate that like your model error, how much error it is there. So I have written the script to just waiting 1 minute. I will just simulate this model. Okay. So now you can see here what happened. Like if you have how we will calculate the error. So whatever the discharge voltage from that profile, we will like associated your voltage will be there with the simulated your voltage data will be there. We are just subtracting. So here we can see here there is a one option of your ANS. So this ANS is basically the data it's related with your simulation. So when I will go through and I will show you like whatever the data it has shown through, I will go through. So I think because of those network problem, it is taking too much of time, or that's why we are not getting. It is still showing like okay. So yeah, through this we calculate our model. Okay, so I will go to next slides. Okay, maybe when it will be simulated, it will pop up in that window only. Okay. So yeah, so what the next approach? So for the next approach, we have checked like it is not fitting very well. So we need to go with like 2 RC. Okay. So with 1 RC, we need to add one another 1 RC branch. Okay. So now how we will go through just in the relaxations regions. Earlier we have gone through for 1 RC model, we have extracted from this model. Okay. So from this region. Okay. Now for your 2 RC, you can go with your whole like whatever the relaxation, the remaining voltage curve is there, you can extract from there. Okay. And with this, you will have an associated transient is there. And there, because you have associated long time constant. Okay. So with, I think it is, okay. So with this relaxation, there will be some associated transient. And because here we have taken like some transient also associated with your 2RC, so we will have a yeah. So yeah, you can see here now I think MATLAB which has simulated the data. So for this DCI profile, what the voltage that difference is there, how much voltage difference is there. So we will just go through like error calculation, and from error calculation we can see here like there is a at a particular these regions we can see here like at a, this region there is some difference is there. Okay, so there is more error is there. You can see here at a lower SOC, the curve is not, it is not overlapping. Okay, so you will observe at a higher SOC there is too much of your error is there. So in the terms of, you can see here like 400 millivolts of approximately you are getting error. Okay, so when you will include more and more number of RC branches, that will pretty well fit your the tested data. Okay, so with your 2RC, you need to consider whole region. Okay, and then with this associated transient, you need to calculate your time constant. So for this time constant, I have gone through. Okay, so what the formula is associated or its expressions or the equations associated with your two RC branches. So this belongs to your one RC branch, and this belongs to your two another RC branches. Whatever the voltage drops across each and every RC branches, then with this thing you will able to calculate your short and long time constant. Okay. So earlier in the I think in the slides I have shown you like with time constant. So you can see here, if you will just go with your one RC model, we only just go with our short time constant. Okay. We are not considering here like those relaxations where the voltage drop will be, or the response is very slow, or the change in the voltage, it will be very less. Those are associated with a long time constant. But when we go with the higher RC branches, like 2RC, 3RC branches, we need to consider this whole relaxation voltage profile also. Okay. So here based upon that, we have also utilized our long time constant. Okay. So T start, T shorten, it will be remain same like as 100. After that, we will go with the long time constant. Okay. And based upon that, we will calculate our time constant for the short time constant, long time constant. And with this, we will calculate our associated R1 and C1. R0 will be remain same. So whatever the your drop is there, it will remain same. So what we are just because we are adding more RC branches, so the sale transient voltage we are just dividing into different regions. Okay. So for the short time constant region, then with the long time constant region. Okay. If you will go with more RC branches, you can take another for another sets of RC branches, another time constant, another MS. But those all time constant will be associated with your long time constant. Okay. So as a conclusion, I will say to you, so when to use your one RC and two RC model, I have already shown it with you, like for like power estimation and the slow physical processes, if you want to observe, one RC is pretty well. But if you go with the more accuracy in your transient, better to go with the more RC branches like 2RC, 3RC. Okay. So what is the application of this model? So application of this model is in your electrical vehicles battery pack simulations. You can also build your model with the battery pack also. Okay. If you have a series in parallel combinations. So for one cells you have model, then all the cells are connected in series and parallels. Those I will plan in the upcoming boot camps. There is one only for the model development. Okay. With like for the battery pack and for the single cell, the same in the series in parallel. Okay. Then this model can be also helpful for your BMS algorithm development and then for SOC and SOS track. Okay. So yeah, thank you everyone for this attending this boot camp. So yeah, if you have any questions and answer sessions, okay, I can see here in your comments there are lots of things is you have put it. Okay. Okay. So yeah, I think someone has put it. Okay. Okay. Yeah, hi Vijay Paul. Audio not clear. Mikali Sapia. Hello, my name is Mikali. Hi Mikali. I'm Jai. Okay. So what is DCIR and ACR? Dinesh Vima. Okay. So what DCIR, ACR is here? So DCR belongs to your the excitation with the DC current. Okay. And ACR belongs to with associated with your AC excitations. Okay. So that's the difference. Okay. Uh, I have gone through like if you want to calculate, but ACR it only shows you because in ACR when we excite only at a higher frequency. Okay. So at a higher frequency, it will perform, or if you are aware of with your EIS, at a higher frequency, your Nyquist plot will cut at your intercept at x-axis. So ACR actually that it only give that value. Okay. So ACR it's give only your ohmic resistance. It will not give about your polarization or the resistance associated with your polarization. Okay. Can you please explain about the TCR pulse test procedure? Yeah, yeah, correct. Fine. So the test procedure is very simple. I've already mentioned like you need to just go with. Okay. So at a particular SOC, you need to fix, okay, yourself. Then you need to write those steps like for your what the duration should be there. Okay. So for the durations, okay, and then the repetitions of your current program. Okay. So those things. The polarization effect is basically suppose that see the thing is that in battery, or you are aware of that lithium ion it's migrated from your cathode to anode and anode to cathode during charging and discharging these processes. So some processes it associated with sudden with your electrode materials. So those will be associated with your ohmic drop. Polarization, those are like which processes this takes more time, like diffusers. It takes more time. Okay. So whatever the resistance it is associated with your diffuser. Okay. So those will be assigned with your polarization effect. Okay, like charged or those things. Okay. So in the voltage profile, you will see those processes, like during those processes, your voltage will not sudden drop. It will take time to like either decay. Okay. So I can show you. It will take you can see it will take like some decay, it is not sudden process. So those are associated with your polarization. Okay. In slide 8, which part of the graph represent RC parameters? Yeah, okay. Uh, Yeah, RC parameters. So I am mentioning this is your pulses. Okay, so in these pulses, it is associated with some voltage changes will be there. So in that, if some sudden changes is there, it will be associated with your ohmic drop and the decay. Not decay, I think it's with slow processes. Whatever the voltage changes it will be observed, it will be associated with the polarization. Okay, same thing when you will just remove the excitation. I think it will in the rest conditions. The same phenomena you will observe here. Like sudden drop will be there, which will associated with the ohmic drop, and these phenomena it will be associated with your like diffusions or those processes. So it is also associated with your polarized spectrometers. And we have extracted those parameters only from that region. Why? Because in this region, when you are performing, at that time your SOC is changing. Like suppose that you have started from 100% and you want to remove in this duration 95%. Still, your SOC is not fixed, like it is at a 98%, 96%, 97%. But now, when you have gone through and you have completed the duration of the pulse, after that, we know your voltage will be at a 95% SOC. So, in these durations, you can extract the parameter because you can see here our cell has reached our desired SOC, and in that desired SOC, there is no that much of change of SOC. So, so it will be accurately to extract the parameters from that region. Okay. How that associate steps such 5% or like that is decided. It depends on you. See, the thing is that uh, I have shown you like in the when you will just go through and if you want to validate your model. So these model validations, it depends highly upon your SOC ranges also. If you will take like 20% ranges, like 100, 80, 60, 40, 20, 0. So you will have a less number of your parameters. So based upon those parameters, you will not get that much of accuracy. Okay. So if you will get with the lesser and lesser SOC ranges, your chances for fitting, okay, or for the simulation data to get more accurately it will be. So that's why I have accepted all the resistance at a 5% of SOC. You can also go with the 2.5%, but you will have a 40 or some more data with you. It will for 5% you are getting 21. So there will be lots of more data with you. Okay. So yeah. Can I get recording for the session? Yeah, absolutely. We will upload. And does RNS equation play a role here? No, no, no. RNS equation is not playing a role here. It is all in your physics-based model. Okay? Equations are confusing, sir. Again, please please. With equations, Satish Singh, can you tell me? Would it be possible to share the model and the read data for practice? Actually, that model we have developed with lots of our like we have gone through. We have hardly worked on this developing the model. So if you want to go with more exploration, how to develop the model, the things in the future upcoming boot camps, I will go through. It will be not possible. Yeah, we Decibels also provide like master certification courses. Okay, so when you can join these master certification courses, we have a one certification battery materials and digital twinning. These courses where we have explore in very detail about from material synthesis to developing model, frequency-based domain modeling, like EIS-based modeling, and electrochemical modeling. If you want to more explore, you can join our courses. Okay. Yeah. And data is not visible properly. Yeah, I know that because of I think that internet connection. What is the practical relevance of this simulation? Yeah, I think Abhidhari Shifa at the end of the in the conclusion, uh, I have written something like what are the applications associated with this model. Could you explain properly what are RC parameters? Yeah, RC parameters. Yeah, I've told you, like this RC parameters, what is there. So yeah, so RC parameters means it's related with your polarization. Okay. So R1 is denote your transient. Sorry, it's denote associated with your charge transfers and diffusion resistance. Okay. So if you have only one RC branch, so R1 C1, it will be associated with your charge transfer resistance and the capacitance, like double layer capacitance, it will form. So it will be associated with you. Okay, if you will consider more and more RC branches, those will be associated with your diffusers. Not yet. What is the RMSE value you have got in there? Yeah, I have got in there. But I think here, just for the simplicity, I have only gone through like model error calculation, just subtraction of your simulated voltage with your real time voltage. RMSE you can also calculate. We have some separate formula. So in that script, you can write your RMS equation. And based upon that, you can also calculate your RMS root mean square error. Okay, great. Can we get the presentation slide? Okay, I will make sure to share this problem. So yeah, thank you everyone. What is the simulation software you? Oh, simulation software, Avilo, Oboshino. Yeah, I have used simulation software MATLAB. Okay, so yeah, thank you everyone. Thank you. It was quick yet insightful. Yeah, thank
Hi.
you. One day possible.
Okay. Hi, Ashutosh. Thank you
Yeah,
for
hi.
today's.
Yeah,
And
yeah.
guys, I have shared the master course link and the certificate link. For certificate, you just have to click on the link and then enroll for the that course. It will prompt you to enroll. Please enroll it and then complete that course. There are 22 sessions. You just have to complete just few clicks and your certificate will be generated. I think all questions are completed, right, Ashutosh?
Yes, sir.
Okay,
Thank you everyone
fine.
for joining this boot camps.
Thank you, Ashutosh, and thank
Yeah,
you everyone
thank you.
for joining in Friday weekend. So, thank you.